Welcome. So we are going to start a new topic today, that is on advanced spectroscopic techniques. We know that nowadays spectroscopic techniques have taken a huge lead in material characterization. That's mainly because we need to know not only the compositions of the different materials we process, but also we need to know the electronic states, vibrational states, and many other features which we will discuss during the process of these lectures. The way I have outlined the different lectures for this part of the course is as follows. Very first, I shall introduce you the electromagnetic spectroscopic theory in one lecture. Then I shall discuss different techniques which are used in the spectroscopic arena. First one is called UV visible spectroscopy. This will take us one lecture. This will be followed by photoluminescence spectroscopy for again one more lecture. Infrared spectroscopy, which is used almost day to day life for the material processing, will take about 2 lectures. Then Raman spectroscopy, which was discovered in 1930s by a Nobel laureate C.V. Raman, will be done in one lecture. And lastly, STEM, the scanning transmission electron microscopic technique, and ELS, energy loss spectroscopic techniques, will be discussed in 2 lectures. I have already discussed about the basics of STEM in the microscopic techniques. I will concentrate the applications of the STEM and followed by obviously the ELS, which is used to obtain different kinds of spectroscopic informations. So in a nutshell, I will spend about 9 lectures in this part of the course. So let us just begin. First thing which I will do is some introduction to the electromagnetic spectroscopic theory. We know that in our curriculum, material science curriculum, spectroscopic techniques are not taught extensively. So you might have got some introduction in some of the courses, but the knowledge of this area in the present curriculum is very small. So, and because this is an advanced course, so we need to first know the basics. As we know that the spectroscopic techniques actually deals with measurements based on light or any other forms of electromagnetic radiation per se, and these are widely used in analytical chemistry for information. Nowadays people use even in other arena also. So basically it deals with interaction with this radiation and the matter, and that is the subject of spectroscopy. So it basically I can tell that spectroscopy is at a very rudimentary level nothing but interaction of the radiations like light, X-ray, gamma ray, or any other part of the electromagnetic radiation with the material, and we analyze whatever comes out after the interaction. EDS, which is used in scanning electron microscopic technique, is another spectroscopic technique where electron interacts with the material and we get signal out of that and then we analyze that. And these techniques actually can give us all kinds of vital information regarding the structure of the material, like molecular atomic species, their structure, electronic structure, band structure, many other things. So therefore we can classify these techniques very easily depending on the type of the region of the electromagnetic spectrum involved in the investigation. And as you know, the electromagnetic spectrum, which is shown here, it spans from radio frequency like very high wavelengths 10 to the power 10 to the power 12 nanometers, or very low frequency, obviously 10 to the power 4 10 to the power 8, to very high energy, that is gamma ray with a frequency of 10 to the power 20 per second or hertz. And so therefore if this is what is the electromagnetic spectrum, we can utilize different part of the spectrum for the spectroscopy analysis, starting from radio waves which are used for nuclear spin states measurements like NMR studies, nuclear magnetic resonance. Then we have IR, which can be used for understanding the molecular vibrations. Then we have a UV visible spectroscopic techniques, which consist of both ultraviolet and the visible range, which can be used to study the valence electronic excitation in the material. And X-rays can be used for core electron excitation, like X-ray spot electron spectroscopy, and many other techniques are there, RGS spectroscopies. So that means, depending on the kind of investigation we would like to do, the uses of the electromagnetic radiation will depend on that. So basically it boils down to the frequency of the radiations which will be used for excitation of the material at the beginning. And so therefore if I go back, so regions from gamma ray, X-ray, ultraviolet, visible, infrared, microwave and radio frequencies, all of these can be used for spectroscopic analysis, but most notable ones are X-ray, ultraviolet, visible, infrared and as well as microwave. So we normally, for a beginner, we differentiate the spectroscopic techniques or classify the spectroscopic technique according to the wavelength of the radiations in this way. Spectrochemical methods, we know that it provides the information like a molecular structure both in quantitative and qualitative way for all kinds of material involved, I think irrespective of inorganic organic compounds. Well, so therefore you know that electromagnetic radiation is used in the spectroscopic technique. So you must have some idea about the properties of electromagnetic radiation. You have studied in your +2 or even in bachelor studies, bachelor's degrees, but I just like to reiterate these issues. Electromagnetic radiation is basically nothing but a form of energy that is transmitted to space at a very high velocity, at the in fact velocity of light, and they can be obviously described by wave, like it has a wavelength, it can be velocity can be related with wavelength and frequencies, and obviously like any other wave it has amplitude, we know that. In contrast to sound waves, light requires no supporting medium, we know that light from sun travels such a long distance without any media. So that means it can pass through vacuum, so there is no problem. And as far as the Planck's theories of the concerned, we can always consider electromagnetic radiation to be consisting of discrete brackets of energy or particles called photons or quanta. We know that the energy is equal to h nu of the photons, where nu is the frequency and h is the Planck constant. So that is again from Planck's theory. And also we know that means what? That means electromagnetic radiation can be either treated as a wave or treated as a particle. This wave dual particle duality is all dealt with in the many of these cases. So by schematic diagram I can say that the light comes, any electromagnetic radiation comes at a a 90-degree angle from the electric field and the magnetic field. So if x and y, y and z are the two directions of the electrical magnetic fields, then the radiation comes in a different this direction, z direction, x direction, which is the known as a direction of propagation. And we can always represent this way the wave. So wave has a particular wavelength w lambda, which is from the tuff to tuff or maybe the peak to peak positions distance, and as an amplitude a, and this is the time or distance which way you can describe. These are all very simple description of the wave. Now if we want to go into some more details, we know the speed of light is fixed. This is given by this value 300 to the power 10 centimeter per second. In a medium containing material or matter, light travels with the velocity less than c because it interacts with the material, and basically the electromagnetic radiation interacts with electrons in the atoms or molecules in the medium, and that is how the velocity of the light gets reduced. Since frequency of the radiation is constant, so therefore wavelengths will decrease as the frequency increases, and when light passes from vacuum to a medium containing matter wavelength will also decrease. Many times we represent wave number mu bar another way to describe the electromagnetic radiations, and this is used in the spectroscopic technique. That is why I would like to know it is nothing but 1 by lambda. So therefore it's a unit inverse of lambda. Lambda is a unit of nanometer, so this is a unit of nanometer inverse, or it can be have unit of centimeter inverse also. That means it has a unit of distance inverse. This is what is shown here. This is the amplitude, this is the distance. As you can see here, the wavelength and amplitude in air is suppose given lambda is to the power 500 nanometers, and when the same radiation enters the glass, the wavelength decreases. From 500 it becomes 330, and subsequently frequency remains same. So that means the energy has changed basically. Energy, sorry, some of the interaction of the material has changed the wavelength, and when it again comes out from the glass, it retains the same wavelength. So these are some of the basic features which we can see nowadays in all kinds of material. And if we want to talk about particle nature, as I discussed that they are photons, so therefore energy of the any kind of radiation can be represented by Planck's law, that is E equal to h nu, which is nothing but hc by lambda, where c is the velocity of light or radiation, and this can be again represent hc nu bar. So this is what nowadays we normally use, hc nu bar is the energy. So if we know nu bar, that is the wave number, we can calculate is the energy, and we know that h is a Planck constant which is a value 6.63 10 to the power minus 34 joule second. So radiation power of any beam, actually beam of radiation, does not matter whether it is electromagnetic or the X-ray or gamma ray or even laser beam, it directly proportional to the number of photons per second. Now as I already discussed the what's called different electromagnetic spectrum region, I am going to tell you the even exact values now. Normally UV ultraviolet comes in the range of 180 to 380 nanometers, visible come 380 to 780 nanometers. Normally you study visible ray comes from 400 to about 800 nanometers, but it can be extended a little bit more. Near infrared comes about 0.78 to 2.5 micron, very large wavelengths. Mid infrared comes 2.5 to 50, and rest is this called microwaves, which are very high wavelengths, maybe of the order of centimeters. That is what I have shown you in this slide. You can see microwaves can have actually 10 to the power 8 almost nanometers, that means about 10.1 meter. Well, now if you go to the molecular structure wise, when a radiation falls on a material, a certain kind of changes happens, and these changes will be depending on the type of radiation the materials are subjected to. That means the wavelength or the frequency of the radiations which is used to probe the material. So if I am going to show you like these things in two ways. One, the type of spectroscopic technique starting from NMR to microwave, infrared, alpha, UV visible, X-ray and gamma ray, and these are all the different what's called parameters. This is the what's called the frequency, you can clearly see 10 to the power 6, 10 to the power 8, 10 to the power 10, up to 10 to the power 8, 18, and energy is starting from minus 3 to 10 to the power 9 energy, that is joule per mole, and wavelength and wave numbers can be calculated very easily. Now if you are basically focusing on very small energy, that is 10 to the minus 3, 10 to the minus 1 joule per second, corresponding to very low frequency or rather very high wavelengths, 10 meter to 100 centimeter, which is used for the microwaves as even larger than microwaves even. So what you see is nothing but change of spin. That is what normally happens quantum mechanically. Spin basically changes when you apply that. So that means you can study nuclear magnetic resonance when as the spin of the both the particles like electron changes depending on the type of material. So we can understand that. Now if we use microwaves, then or even infrared, which comes in the frequency 10 to the power 10 to 10 to the power 14 in this range hertz, So you can have basically change of orientation of the molecule. So that's what is shown here. You can have this kind of molecule, suppose big atom, small atom connected by a bond, they can get differently oriented, or you can have a geometrical change of the configuration. So this is what is normally happens when you use this in this range, any kind of radiation whose frequency varies in this range. Now if you go to higher frequency level, little higher, 10 to the power 14 to 10 to the power 16, then you can have basically changes made in terms of electronic distribution in the material. That is what is shown here. You can see the electronic distribution can get modified, and that can be studied. And if you go to very high energy like gamma rays, 10 to the power 18, which correspond to 100 picometers of wavelengths, energy is 10 to the power 9 joule per mole, you can have even change in the configuration of nuclear configuration. That is what we know. If we bombard gamma rays into certain materials, nuclear configuration gets changed. You can create voids even in the material by removal of the material. These are all very well documented in the literature. So upon knowing these aspects, let us now look at what actually spectroscopic technique does really. Because as I told you at the beginning and for the last few slides, that we use certain electromagnetic radiation and allow it to fall in the material, and then see the changes happen in the material in terms of when the radiation comes out. So spectroscopics actually use these interactions. So in this case, sample is stimulated rather by applying energy in the form of either heat, or you can apply electrical energy, or even light actually, or even you have a chemical reaction. So basically any kind of sample is stimulated by these energy sources, and it is, you know, that at the beginning we assume that analytical solutions or the material is in the ground state. So therefore lowest energy state. Therefore as I stimulate it with energy or with certain kind of energy source, it will cause this material to undergo transitions. That is, it is expected that energy will make the material to go from ground state to higher energy state or excited states. So if this is what actually perceived to be happening in the material, then we can obtain information of the analytic material by measuring the electromagnetic radiation that will be emitted when it will return to the ground state. Because if we excite any materials by energy to high energy level, then obviously after certain time the material will come back to the ground state or the low energy state, and extra energy will be emitted. So we can actually then measure the radiation emitted as the material comes back, and by measuring the amount of the electromagnetic radiations and also type of radiations coming out, absorb, we can get a lot of information about the material. So that is in a nutshell, very simple way any spectroscopist does in the laboratory. Now depends, obviously then depending on that we can have different kinds of techniques. In emission analytical, basically the sample is stimulated by heat or electrical energy or chemical reactions, and this is called emission spectroscopy. So normally the stimulus is heat and electricity in this emission spectroscopy. Then you can have chemiluminescence spectroscopy. That means in this case the sample is excited by chemical reactions, not by heat or electrical energy, but the chemical reactions. That is why it is called chemiluminescence spectroscopy. So measurement of the radiation power emitted when the material comes back to the ground state can be used, both the cases, to measure, identify the concentrations. And results of these measurements are basically has to be represented by a graph or spectrum, which we will see in few minutes time in some of the plots. And these cases, this is the y-axis can be any parameter as whatever radiation coming out, and x-axis will be either lambda or 1 by lambda. So lambda is wavelength, 1 by lambda is wave number. Let us see the sum of the things. Suppose we have a sample like this, and we have a energy source, thermal, chemical or electrical, and we are excited the material. Once you excited the material, obviously sample will absorb the energy, certain part of energy, and it will go to the high energy state as I said, and then it will come back to the ground state after certain time, and in that process it will emit the radiation. That is what is known as PE here. Okay. So, photoluminescence, whatever you can say, that it is PE. Now, if I go back to this place, this one, the energy states here. So, suppose 0 corresponds to the ground state, and now I have energized the material, excited the material, so that it can go to the higher energy state like 1 and 2, which are the excited states, and as after certain time when it comes back to the ground state, it can have different paths. So, this is the excitation to go to suppose state 1, this is the excitation go to suppose states 2. Now, very fast thing can happen is basically it can come back from state 1 to the ground state, and which correspond to energy emission of E1, or can be related to H nu 1, or can be related to Hc by lambda 1. Okay, second thing can happen basically that from the energy stage 2, if it excited, it will be given so much energy that it go to energy stage 2, and it comes back to the ground state, and then this much of energy will be released, E21, and which correspond to Hc by lambda 21. Sorry. So, in this case it will be E2 will be emitted, not E21. E2 will correspond to Hc by lambda 2. You can have an inner transition, that is from 2 state to 1 state, excited 2 to excited 1. In that case energy will be released like E21 with a wavelength given by E21. So, as you can see here, the energy U1 is obviously higher than E2. Okay, the amount of energy is, sorry, E2 is higher than the U1 and then E21. You can see the length of the arrow and determine that also, that is expected, understandable. So, if I plot P versus lambda, which is done in this case, that is what is the plot, a spectrum we call, and you can see we get peaks corresponding to lambda 2, that means this is corresponding to transition from 2 to 0, then another peak corresponding to lambda 1, this corresponding to transition from 1 to 0, or we can have a very small peak corresponding to transition from 2 to 1. So, these are all marked like lambda 2, lambda 1, lambda 2, 1. So, that means these are the characteristics wavelengths which will decide the type of material we are probing. So, these wavelengths once we know, then we can actually probe, we can say that what kind of material it is, what kind of states the material has, all these kinds of features can be done. So, these are all very simplistic way of plotting the data or doing the measurements. Now, we can actually have something like absorption instead of emission. So, when a sample is stimulated by application of an external electromagnetic source, several processes are obviously possible, and you know some of the incident radiation can be absorbed, and then this absorbed radiation can promote the species to go to the excited states. And in absorption spectroscopy, which is just I have shown you in the last slide, the amount of light absorbed is basically a function of wavelengths, and it can be measured, and then obviously we can use both these wavelengths, qualitative measurements with type of material, and the area under these curves will give us the amount of energy released, okay, at that particular wavelength, and that can be used for quantitative analysis. In a photoluminescence spectroscopy, emission of photon is measured following this absorption. The most important form of photoluminescence spectroscopy is fluorescence or phosphorescence spectroscopy, which we will discuss in later. Well, this is what the absorption looks like, that the last one was emission. Absorption is like this. So, we have incident radiation P0 of intensity, it falls on a sample, and then P is the transmitted radiations, and we can assume that initially the sample was at ground state. Once the radiation is absorbed in the material, it can go either to the state 1 or state 2. So, this is the transition from 0 to 1, the transition from 0 to 2, and then we can basically measure A, this is the absorption as a function of wavelength lambda, and we are going to get 2 peaks again, or 2 peaks corresponding to lambda 2 and lambda 1 corresponding to excitation from 0 to 1, lambda 2 corresponding to excitation from 0 to 2. So, this is absorption. Once something getting absorbed, we can actually measure the absorbed energy as a function of wavelength and find out the whole characteristics of the whole process. Well, another one is luminescence, as I said. So, you have suppose incident radiation P0 falling on the sample, okay, and then some part of the radiation will be transmitted and some part will come as a luminescence. Well, luminescence means some kind of inside transitions, and which we will just discuss, and then you can measure this luminescence as a function of lambda. So, I have discussed emission, I have discussed absorption, now I am discussing luminescence. So, in a luminescence, again we can consider sample at the beginning to be at ground states, and once you energize, it can go absorb energy and go to state 1 or state 2, okay. And then you can have different kind of transitions. Obviously, first one transition can happen is basically from 1 to 0 when it comes back to ground state, or your second one is 2 to 0, or even you can another way you can have is from 2 to 1. This dotted arrow is basically talking about the transition, suppose from 2 to 1 followed by 1 to 2, 1 to 0. So, and all these things come as a specific wavelengths, and we can actually get this wavelengths very easily. The area under the peaks tells you how much is the energy comes out as a function of as a luminescence. So, we will discuss more detail about now absorption process. Absorption is very important part of the spectroscopics. I have shown you 3 different types of processes: emission, absorptions, and the luminescence. So, absorption process is always discussed in terms of Beer's-Lambert law or Beer's law. Many times people call it Beer's law, many times people call it Beer's-Lambert law, but both of these scientists were involved. This law, if I look at it, it tells us exactly how the attenuation of this energy depends on the concentration of the absorbing molecule and the path length over which the absorption takes place. Obviously, in a solution or in a material, if it is not 100% pure, there will be concentrations of different kinds of species presence, and the attenuation of energy, that means how much will be absorbed, how much will be emitted, how much will be having photoluminescence, will depend on the what's called both the concentration of the absorbing molecule and also the path length. So, how we can show this? Schematically, this can be shown like this. Suppose you have parallel beam of monochromatic radiation lambda, it forms and falls on a solutions and it passes through, and the thickness of this absorbing solution is B and the concentration is C moles per liter, B is terms of centimeter. Because of the interaction of this energy with these solutions, okay, that means interaction of the photons of the radiation with the molecules or the material inside absorbing the particles, the radiation power of the beam will decrease from P0 to P. So, we can define the transmittance actually T like this ratio P by P0, and absorption is basically the log of P0 by P, the opposite. Now, so again I am doing that. The transmittance is basically fraction of the incident radiation transmitted by the solution, and it is often expressed as a percentage transmittance, that is T equal to P by P0 into 100, and absorption is basically related to the transmittance in a logarithmic scale, or that is log of minus log of T, that is log P0 by P. Remember, this is P0 by P, transmittance is P by P0, that is the difference. So, minus log T is absorption, so that is the relationship between T and A. So, this is how they are related. Now, ordinary transmittance and absorptions cannot be measured the way I have told you, just showed you. Okay. So, that means, what do I say? The cannot be measured as shown because the solution to be studied must be held in a container. We cannot simply take the solution and float it in air or in a vacuum and then measure. We need to keep the solutions in certain container, and that means that whenever you keep it in container, you will have the problems of container coming to picture, like you have reflections or scattering losses from the cell walls or the container walls, and these losses may be substantial. Then one has to take care of those losses. Light, for example, can be scattered in all directions from the surface of large molecules, even particles such as dust or even solvent, and this can cause further attenuation of the beam, there may energy loss or energy absorbed or whatever as it passes through solutions. So one actually needs to take care of those. How to take care of those? Or let me first show you different processes. Suppose you have incident beam Pi, then you can have reflection losses, you can have scattering losses, you can have reflection losses at the even interface, or you have a foreign particle inside or a big molecule inside, you can have these processes taking place again. So to compensate these effects, how to take care of this, power of the transmitted beam, power of the beam transmitted to this cell or the container is compared with one that traverses an identical cell containing only solvent or a region blank. So basically you are using a standard. So an experimental absorption that closely approximates the two absorption of the solution can be obtained. So that means you can write absorption equal to log P0 by P, approximate equal to P solvent by P solution, if you have this kind of container which contains only solvent or the reagent. So that is how one can take. This is very simple to describe, I do not need to go in detail of that. Now after knowing all this stuff, let us know what is Beer's law actually. The Beer's law, or according to this law, absorption A is directly proportional to the concentration of the absorbing species C and path length P of the absorbing medium. So that means A is directly proportional to C, that is the concentration of the absorbing species, and A is directly proportional to B. B is nothing but the path length. Okay, so that is what I can write down, and C is basically concentration. So A can be written as equal to A into B into C, where A, B into C, A is a proportionality constant, and this is known as absorbability. Because absorption is a unitless quantity, A, A has no unit, is a logarithm, and logarithmic of any number has no units. So therefore the what's called C and B should have the units which will cancel out. C has a unit of gram per liter, B has a unit of centimeter. So therefore absorbability should have a unit of liter per gram per centimeter, otherwise capital A will never be unitless. This is what is called Beer's law or Beer-Lambert's law, whatever you can say in the literature. This is very simple, straightforward. Absorption proportional to C, absorption proportional to B, path length. So therefore absorption equal to A into B into C, where A is a constant called absorbability, B is a path length in centimeter, and C is the concentration in gram per liter. So when we express the concentration in mole per liter, B in centimeter, the proportionality constant is sometimes called molar absorbability, and then it can be given a symbol like epsilon, and A equal to this formula, and obviously epsilon will have units of liter per mole per centimeter. Now one can actually apply this is to a mixture. This is nothing but additive, this law. So Beer law can be applied to any solution containing more than one kind of absorbing species or a substance. Obviously we need to consider the fact that there is no interaction between these species. So total absorption is nothing but the summation of the individual absorption. So that means I can write A total is equal to sigma I equal to 1 to n AI. That is what I can say, and this is very straightforward. Now, so that means one can actually study the absorption process by using Beer's law, and there are advantages of using this. This is very simple and straightforward law, but one has to also know what are the limitations, that so that you can take care of. there are few exceptions to these linear relationships between the absorption and the path length at a fixed constant. As I said, A equal to A to B into C, therefore for C1 A1 A is equal to B. This is the linear law. We frequently observe the deviations. Deviations are seen and observed, just like deviation in Raoult's law, all of you know. Raoult's is also linear law, but there are deviations here also. And these deviations can be either real deviations, which are fundamentals, and we need to talk about these limitations very clearly. You can also have limitations as a coming consequence of the absorption measurements, like as a result of chemical changes associated to the concentration changes. There can be instrumental deviations or chemical deviations. So, we will discuss one by one. First and foremost one is the real deviations. As I said, the Beer's law describes the absorption behavior of a dilute solutions only, first for your kind information, and it is a very limiting law like Raoult's law. As concentration exceeding about 0.01 molar, average distance says between the ions and the molecules are diminished to the point where each particles affect the charge distribution and thus the extent of absorption of its neighbors. So, that means if you have a species in a solution whose concentration is more than 0.01 molar, Beer's law cannot be applied to that. So, that means Beer's law can be applied only for solutions or the species in the solution whose concentration is very small. The occurrence of this phenomenon causes deviations. Whenever you have concentration more than 0.1, it can cause deviations between the absorption and the concentration, and when even ions are in close proximity, the molar absorbability of the solution of the analyte can be altered because of electrostatic interactions, and this can also lead to departures, but this is not widely absorbed. This is very prominent things. You can have chemical deviations, as I said. So, deviation of Beer's law can also appear when absorbing species undergoes dissociations or associations or even reactions with the solvent. That means if there is any reaction of the chemical species, either it is a dissociation or reaction, does not matter, it will give you different values of absorption than if there is no such a kind of reactions, and when this will lead to departures, and such a kind of departure can be predicted obviously by looking at the molar absorbabilities of the absorbing species, and if we know that, and obviously we should know also equilibrium constants. Unfortunately, we are unusually unaware of such processes at the beginning. Okay, we do not know that, and so compensation is now very impossible. Typical equilibria that gives rise to this kind of things are actually monomer to dimer in polymers, metal complexations, or when more than one complex is present, acid base equilibria, solvent analyte associations equilibria. So, these are the things you should remember which can give rise to chemical reactions.